All right, guys, as I was correcting your work one, I saw so many errors on number 5. I wanted to go over number 5 and 6 and 8 with you because all of those had difficulty. So Bill's pushing this crate up this ramp, right, that's 5 meters high. And the ramp has a mass of 35 kilograms. Okay. Now, since there's no friction on the ramp, the work he does on it will equal its change in gravitational potential energy from the bottom to the top. Okay, and we know that the change in gravitational potential energy just equals the weight mg times the height. Or I guess on your formula sheet, that's mg delta y. So we can just substitute 35 kilograms. Please start using your units and your calculations. 10 meters per second squared. They will be taking off, by the way, on the AP exam if you don't use those units or have those units in your final answer. Delta y is 5 meters, and we would just multiply all of those to get 1,750 joules. Gravity is acting in the opposite direction. Gravity's work is negative because our motion is upwards, gravity is downwards, and so part B, when it asks for the work done by gravity, it would actually be a negative 1750. For number 6, though, and by the way, you can solve number 5 like we're going to solve number 6. It's just more difficult, so why do it? Why do it that way? So Bill is pushing up the ramp with a certain force. We don't know what that force is. We do know that the ramp is being supporting the block, so there must be a normal force. We do know that that same block that has a weight of 350 newtons, right? That's how much 35 kilograms weighs. And we do know friction is acting as well because they give us the coefficient of friction. Friction does not equal the coefficient of friction. It equals the coefficient of friction times the normal force. A lot of people are just saying friction was 0.585 here. It's not. It's 0.585 times the normal force. Well, what is the normal force? So we have to break down the gravity vector here into its x and y components. And I've made my x and y parallel and perpendicular to the ramp. So this is a 25-degree ramp, so that is a 25-degree angle there. This one is 350 times the sine of 25 degrees. And this one is 350 times the cosine of 25 degrees. Why is it important to find both of those? Well, I'll tell you why. Because the net force in the y direction is 0. Y is perpendicular to the ramp. We know it's not accelerating into or out of the ramp. And so that's going to help us find out what the normal force is. Since the normal force and this component of gravity are the only y components and they're in opposite directions, they must be equal and opposite to one another. So if we do 35 cosine of 25, we get 317.2 newtons. So I know that is my normal force. That's going to be important because friction is fun. It is mu times the normal force. So I'm going to take 0.585, which is my coefficient of friction, multiplied by 317.2 newtons. Coefficient of friction has no units. It's just a ratio, 585. And that gives me 185.56 or 186. Let's just round that, 186 newtons. Okay, so we know that if we're pushing it up at a constant rate, let's assume he's not accelerating up the ramp, that the friction must at minimum just balance out the friction and the force of gravity pulling it down the ramp, which, by the way, we should find out what that is, 350 times the sine of 25. And that will give us roughly 148 newtons. Okay, so the forces up the ramp must balance out the forces down the ramp, so my force that Bill applies in part A must equal the friction and the gravity that's in the x direction, which would be 186 newtons plus 148 newtons, which would equal, I don't know, a lot of newtons. It would equal 334 newtons. Okay, whoops, that's not on the page, my goodness. Okay, now that we know the force pointing down that Bill applies to the box, we can figure out the work that Bill the work that Bill does on the box, right? Because work is just force times distance times the cosine of the angle between them. Here, the thing you need to be careful of is that the force of 334 newtons that he applies along the ramp, which, by the way, is 11.8 meters long. You can use your trig to figure that out. The angle is not 25 degrees, right? He's pushing up the ramp. The displacement is up the ramp. There is 0 degrees between parallel to the ramp and parallel to the ramp. So it's the cosine of 0 degrees, which happens to be 1. So we'll take that, the force, and multiply it by the distance, and we should get 3,940 joules. How much work is done by friction? My goodness, I'm going to have to hurry up because you can hear that's the bell. I've got a class coming in. Well, friction, we've already established, was 148 newtons. We're still going to use the same formula, right, because we're looking for work. It was 186 newtons. And that was also applied over 11.8 meters, but the motion is up the ramp, friction is down the ramp. The angle between up and down is 180 degrees. And so we should get a negative value here, which makes sense because friction takes energy away from stuff. So we should get roughly 2,195 joules, but it should be negative, right? The cosine of 180 will make it negative. And number 8 we'll have to continue at another time.